Hi guys, welcome back to our channel Unknown IITians. Today we are going to discuss about set theory. Today we are going to cover set and their cardinalities, subsets, operations performed on sets, Venn diagrams, Cartesian product, relations and their types, functions and their types. So let's get started. Firstly, what is a set? Set is collection of some objects. So basically, let's take an example. Here this is X is a set of some collection of some numbers. So this is considered to be a set. This is the way we represent a set. So number of elements, so this 1, 3, these are considered as elements in a set. So the number of elements in a particular set can be infinite. There is no restriction on number of elements in a set. And order also doesn't matter. It can be in any order. So for example, let's consider another set. 1, 3, 2, 5, 8 and 7. This is also considered as a set. Here we took a collection of some numbers with no order, but still this is considered as a set. So set is a collection of objects and with no restriction on number of elements. There can be infinite number of elements. For example, set of natural numbers, all natural numbers, set of all whole numbers. Even these are considered to be sets with infinite number of elements in it. Okay, next. What is cardinality? Cardinality is the number of elements in a set. Here we are given an example of set 1, 3, 6 and 7. This set is containing 4 elements. So the cardinality of the set is 4. So the number of elements given in a particular set is considered to be cardinality of that particular set. This can be 0, 1 and so on up to infinity. As we have discussed, there is no restriction on number of elements. The cardinality of a particular set can be infinity. And coming to this statement, not every collection of items is a set. So as we have discussed before, set is defined as collection of some objects. Okay. So let us consider an example. If here we are given top 5 favorite colors are yellow, blue, green, red and white. This is given as top 5 colors. This is not considered as a set because this top 5 is not for everyone. This is just based on one's opinion or some group's opinion, but this is not always correct. So such examples like top 10 art heroes, top 10 movies, top 10 colors, these kind of examples are not considered as sets. And coming to subsets. What are subsets? Subset is a sub collection of a set. For example, let us consider a set 1, 2, 3, 4, 5, 6. Then we consider one more set 1, 3 and 5. Now can we say B is subset of A? Yes, because all the elements in B are also elements in A. 1, 3 and 5 belong to 1, 2, 3, 4 and 5, 6 this set. So B is considered to be subset of A. We can denote it like this. This symbol represents B is subset of A. So here we are given a diagram. Let's look into this. Here a set of real numbers. set of real numbers is given. Natural numbers is a subset because all the natural numbers are considered to be real numbers, and whole number is also a subset of real numbers, and natural numbers are subset of whole numbers because whole numbers is a set of numbers starting from 0 to infinity, whereas natural number starts from 1. So there are common, all the elements present in the natural number set are also present in the whole number set. So this is subset of whole numbers. And next, integers. Integers is subset of real numbers, and natural and whole numbers are considered to be subsets of integers, as integers involve negative numbers as well. And next, coming to the rational numbers. Rational numbers is a subset of real numbers, and all these natural, whole and integers are considered to be subset of rational numbers because it also involves the fractional values in it. And there is some other set called as irrational numbers, which is subset of real numbers but not a subset of not a subset of rational, integer, whole and natural numbers, and this is a separate section. This is a subset of real numbers. Okay, this is one of the example for subsets. What is a proper subset? Here we can say that every set is subset of itself because every element in this particular set will be element of that set itself. So then what is a proper subset? Proper subset means all the subsets of a particular set except itself are considered to be proper subsets. All the subsets which are not all the subsets which are subsets to the given set except itself are called proper subsets. Okay, next coming to empty set. Empty set. This set will not contain any element. Okay, the number of elements in a set is 0. If number of elements in a set is 0, then that particular set is considered as empty set. So in previously we have discussed empty set. Then we have one more set called null set. Null set will contain one element. Okay, empty set and null set both are different. Null set will contain a single element, but empty set will not contain any element. Next, power set. Power set is defined as set of subsets of a set. For example, we are given a set 1, 2 and 3. Now, what is a power set? It is power set. It is collection of subsets of this set. So 1 is a subset of this set, 2 is subset of this set, 3 is subset of this set, 1 comma 3, 1 comma 2 and so on. The all possible subsets of this particular set are the elements of this power set. So power set is defined as collection of subsets of a given set. So how to find number of elements in a power set for a given set? What is the formula for number of elements? 2 power n, where n is cardinality of given set. So for example, we are given a set containing elements 1, 2, 3. So the cardinality of this set is 3. So the number of elements in this set's power set is 2 power 3. That means the power set will contain 8 elements. Okay, every power set will have a null set. Null set is subset of every set. Okay. Next, let's we perform some set operations. So here we are given set A and set B, for example. So we are given elements 1, 2, 3 in it, 1, 3 and 5 in it. Okay. So union of these two sets is set of all the elements in these two sets. That means 1, 2, 3 and 5. See here, set A is containing 1, 2, 3 as elements. Set B is containing 1, 3, 5 as elements. So union of these two sets means the set that is containing all the elements in the both sets. So if there are some repeated elements in both the sets, then they are counted only once. See here, 1 and 3 are present in both the sets, but here in the union set we return those elements only once. Okay. Then what is intersection? Intersection is considered to be the common elements in the given two sets, 2 or 3, any number of sets. The common elements are considered to be intersection. So for example, we are given a set 1, 2, 3, 4, 5 and 6. So what are the common elements in these two sets? There is no common element, so these are represented in this way as there are no common elements. For example, let us consider the previous set 1, 2, 3, 1, 3, 5. Here 1, 3 are the common elements for both the sets. So this set is represented as 2, 5, 1 and 3. So this represents the intersection. This represents the intersection of the two sets. Okay. Next, what is set difference? Let us consider the previous example itself. The set 1, 2 and 3. 1, 3 and 5. So the set difference means that the elements that are only present in a given set. So for example, here we are having A minus B. That means we consider the elements that are present only in A. That means let us draw the Venn diagram. 2, 1, 3 and 5. So this is the set of A minus B. So the elements that are present only in A, that means these elements are not present in B. So the elements will not belong to B as well as A intersection B. The elements will only belong to A. So for example, if we are asked to calculate B minus A, then we have to consider the elements that are present only in B. but not in A intersection B, and also not in the set A. The elements must be present only in the set B. That is considered as subset difference. Next, what is complement? See, here we are given a diagram. Okay, this is set A, and this is considered is to be some universal set. What is universal set? Universal set is a set that contains all the existing sets in it. So the universal set will contain all these existing sets as its elements. Okay, so this is A. A is considered to be, every set is considered to be subset of this universal set. Okay, now the shaded area is considered to be the complement of set A. That means complement set is a set that contains elements which are not present in that particular given set. Like that means, sorry, I gave a mistake. Complement of a particular set is defined as a set that contains all the elements except the elements that are in the particular set. See, for example, here we are having set A. Let us consider A is 1, 3 and 5. So now complement of this set will be the set that containing all the elements except 1, 3 and 5. That is considered to be complement of A. See, that can be represented as set that not belongs to set A. Okay, as we have discussed how to represent set using Venn diagram, now let's solve a question. We are given total 1000 students. Okay, and 800 students enjoy learning English. Number of students enjoy learning English are 800. 700 students enjoy learning history. Number of students enjoy learning history are 700. 500 students enjoy learning both history and English. That means intersection of English and history subjects are 500. These 500 students are interested in learning both English and Hindi. Okay, how many students enjoy learning about English but not history? And how many students do not like history, do not like English nor history? Okay, so let's solve this. Let us draw a Venn diagram. Okay, there are 1000 students. Okay, we have two subjects, English and history. Number of students like to learn English are 800. Okay, English, number of students like to learn English are 800. Number of students like to learn history are 700. Who like both are 500 students. Okay, now am I correct? Yeah. Now we have to find number of students who enjoy English but not history. Who will who like English but they did not enjoy history. That means we have to find E minus H. Only this set of students. Am I right? Okay. So now N of E, number of students who like English are 800, and number of students who like both English and history are 500. So this whole English is 800. Only this intersection is 500. That means number of students who like only English are 800 minus 500. This total set, this total circle represents 800, whereas this small intersection part represents 500. We want this value, the remaining part of the circle. That means 800 minus 500. Totally 300 students like only English but not history. Okay. Next. The next question. What is the next question? How many students do not like English nor history? Okay, that means we have to find this set, complement of the given two sets. Okay, let's draw the diagram again. This is English and this is history. So now we have to find the students who don't like both English and history from the 1000 students. So total number of students are 1000. From that we have to subtract number of students who like to learn English and number of students who like to learn history and number of students who like to learn both. So then that will give you the students who like the neither subjects. Okay, so as we have done in the previous question, number of students who like only English are 300, right? Number of students who like both are 500. Number of students who like only history are H minus E. That means 700 minus 500. Only 200 students like history. So now we have to find the shaded region. That means we have to subtract these elements from the 1000 elements. So 1000 minus 300 minus 200 minus 500. That means 1000 minus 1000, that is equal to 0. That means there is no student in the whole set of 1000 students who like neither English nor history. So now from this problem we have learnt a new formula that n of a minus b is equal to n of a minus n of a intersection b. So let us once again understand through a Venn diagram. This is set A and this is set B. As we have seen in the definition, A minus B means the elements only in set A but not in B. So this shaded region is what we want. So now n of A n of A means the whole circle, which will include the only elements present in A and intersection of both the sets. So now if we subtract the intersection from the total elements of A, we will get the number of elements present only in A but not in B. Okay. So now let's discuss some important formulas of set theory. So n of A union B is defined as number of elements present in A, number of elements present in B minus number of elements common in both the set A and B. So let's look at a Venn diagram to understand it better. Given a set A and set B, union is defined as the number of elements present in both set A and set B. So the shaded area is the union. So that means number of elements present in A. This circle represents the elements of A, and this circle represents elements of B. But here we are adding this common part twice, so we have to subtract it. So that gives n of A union B. For example, if there is no intersection, the sets are like this, then this is 0. If there is no intersection, number of elements common are 0. So n of A intersection B will be n of A plus n of B. Okay, that is what given in this formula. Similarly, we use this formula in our previous question. N of A minus B is equal to n of A minus n of A intersection B. See, once again we'll see it. For example, we are given two sets A and B. Just want the elements present in A but not in B and intersection of both. So n of A minus B will be is equal to n of A. That n of A represents this whole circle, and just we want the shaded area, so we have to subtract the intersection part from the whole set A. So that will give us number of elements that are present only in A. Similarly for B, that means n of B minus A will be n of B minus n of A intersection B. Okay, and here this is for formula for when there are three sets in union of three sets. Okay, next we are going to discuss about relation. So basically, what is a relation? The relationship between the sets of values is defined as a relation. So here in the example we are given two sets x, y and z, 1, 2 and 3. These are the given sets. So the relation between these two sets, the relationship between these two sets is defined as relation. In mathematics, relation is between x values and y values of ordered pairs. The set of x values are the domain. The set of the y values is considered as range. So here the relation is between x, y, z set and 1, 2, 3 set. So this x, y, z set is the domain. These are the x values. whereas the 1, 2, 3 are the y values. That means the set is range. Okay, so this is the basic definition of what relation is. Now coming to the Cartesian product will give you the all possible relations for a given two sets. So here we are given x, y, z and 1, 2, 3. So the all possible relations for x, y, z and 1, 2, 3. So x can have a relation with 1, with 2 and with 3. Similarly, y can have a relation with 1, with 2, with 3. Similarly with z. So here we are given x1, x2, x3, y1, y2, y3, z1, z2, z3. So these are the possible relations for a given, not for a given set, for two sets. Reflexive relation is a binary relation on a set A which satisfies the given condition. This means that every element in a given set A is having a relation with itself. So this is defined as a reflexive relation. Let us consider an example. Given set A 1, 2, 3. So let's define a relation. A is related to A. So the relation is 1, 1, 2, 2, 3, 3, 3, 1, 2, 1. So now this relation is a reflexive relation because it is having 1, 1, 2, 2, 3, 3. So all the elements in A are mapped to themselves. So the particular relation is a reflexive relation. So now what is the difference between reflexive relation and identity relation? So now let's look into that. Reflexive versus identity. Reflexive relation. Every element is related to itself. Identity relation. Every element is related to itself only. So this is what the basic difference is. So as we have seen in the before example, the relation we defined is having elements apart from 1, 1, 2, 2 and 3, 3. We have 2, 1, 3, 1 also included in the given relation. So this particular relation is defined as a reflexive relation. This is reflexive relation because all the elements are mapped to themselves. So the condition for a reflexive relation is just this. So if you have any other relations apart from this, then also that is okay. But coming to identity relation, this is not possible. Only 1, 1, 2, 2 and 3, 3. These must be the relations. Okay. In the relation set, only the elements mapped to themselves must be the elements defined. If you are having any extra element, then that is not an identity relation. That is the difference between reflexive and identity. Next, symmetric relations. Symmetric relation is a type of binary relation where one side is mirror image or reflection of the other. So here what the meaning is, for example, in a given relation set, if you have 2, 3, then you must have 3, 2 also. If this condition is satisfied, then that is treated as a symmetric relation. That is what given here. The relation is equal to If A equal to B is true, then B equal to A is also true. Similarly, if 2 related to 3 is there, then 3 related to 2 must be there. That is a symmetric relation. So let's see an example. Now we have same set 1, 2, 3 and the relation defined as this: 1, 2, 1, 3, 2, 2, 2, 1, 3, 3 and 3, 1. So now this relation set is a symmetric relation because here we are having 1, 2 and also 2, 1. Here 1, 3 is there as well as 3, 1 is also there. Then what if we have something like this: 2, 2 and 3, 3? There is no other thing like again 2, 2 is not required. Here if we even take the other way, like A is equal to 2, B is equal to 2, if we reverse it also, we will get the same element. So 2, 2, 3, 3 alone are enough. But coming to 1, 2 and 1, 3, 2, 1 and 3, 1 must be present in a given relation. Then that is treated as a symmetric relation. For suppose if 3, 1 is not there, then this particular relation is not a symmetric relation. Okay. Next, a transitive relation. What is a transitive relation? For example, in a relation set, one element is 2, 3 and the other element is 3, 1. Then if there is an element 2, 1, then that is a transitive relation. Here it is given: x is related to y is related to z and x are related. Okay, this is a transitive relation. Next, antisymmetric relation. An antisymmetric relation is just opposite to a symmetric relation. In a set A, if one element is less than the other, satisfies one relation, then other element is not less than the first one. Okay, so here the meaning is, for example, we consider the relation A greater than B. These are the elements of set A. So, for example, let us consider like this: 1, 2 and 3 and one more 1, 2 and 3. So now the relation is A greater than B. So then 1 can map to 2, 1 can map to 3. 2 can map to 3 alone, but 3 is having no mapping because 3 is the greatest number. So the elements of this particular set are 1, 2, 1, 3, 2, 3. That's it. Here we cannot write 2, 1 and 3, 1 as elements because 1 is less than 2, but let us consider this is less than 1 is less than 2, but 2 less than 1, this condition is not satisfied. So if 1, 2 is a relation, then 2, 1 cannot be a relation. Similar way for greater than and similar way for minus. So this is anti-symmetric relation. In symmetric relation, if 1, 2 is present, 2, 1 must be present, but in antisymmetric, it should not be there. Okay. Next. So here is the difference between symmetric and antisymmetric relations. If A B belongs to the relation, then B comma A must be belonging to that relation. Here, for symmetric relation, we have an example of addition. So in the previous example itself, we consider a set A plus B is equal to 3. So let us consider this is the relation that we want. Then 1 will have a relation with 2 and 2 will have a relation with 1. So the relation set is 1 comma 2 and 2 comma 1. So this is a symmetric relation. For example, if we have the condition as A minus B is equal to 1, then we have, let us use another ink. 2 will map to 1, 3 will map to 2. So the relation set is 2 comma 1 and 3 comma 2, but 1 comma 2 and 2 comma 3 are not allowed. So then this is an anti-symmetric relation. That is a basic difference between a symmetric and an anti-symmetric relation. Next, equivalence relation. Equivalence relation is a relationship between elements of a set that has the three properties: reflexivity, symmetry and transitivity. That means a relation which is symmetric, transitive and reflexive, that is considered as an equivalence relation. What is reflexivity? For all A in set, A is related to A. What is symmetry? If A is related to B, then B is related to A. What is transitivity? If A is related to B and B is related to C, then A is related to C. So if these three conditions were satisfied in a given relation, then that is treated as an equivalence. Now let's discuss the topic functions. Function is defined as a relation between two given sets where the elements in the domain set is mapped to exactly one element in the codomain set. Only one element, the element in the domain set, is mapped to exactly one element in the codomain set. So here we see an example. B is mapped to 2 as well as 3. This is not an example of a function because the element in the domain set is mapped to two elements in the codomain set. Okay, so now let's discuss the difference between domain, codomain and range. So domain of a function is defined as the set of all possible inputs. The set of all possible inputs of a function is defined as a domain. What is codomain? Codomain is a set of all possible values that can be attained by the values in domain. So here this is the domain and this is the codomain. So these are set of all possible values. Then what is range? Though here this is a codomain is set of all possible values, then range is the set of the values that are assigned to the elements of a domain. Now let's look into different types of functions. We have 4 different types of functions in total. one-to-one function, many-to-one function, onto function, and into function. So now let's discuss them in detail. First, injective function, which is also known as one-to-one function. It is a function in which every element of a domain is mapped to single element of codomain. That means no two elements in a domain are mapped to single element of a codomain. So here we are given an example. 10 is mapped to 1, 20 is mapped to 2, 30 is mapped to 3. But in the second example, both 10 and 30 are mapped to 3. So this is not an injective function. Every element in the domain is mapped exactly to single one, and that is unique for every element in the domain. So now let's look at two examples. F of x is equal to x and f of x is equal to x square. Now let's consider a small set 1, 2, 3 and the the range. 1 will be mapped to 1, 2 will be mapped to 2, 3 maps to 3. So here every element of the domain is mapped to a unique element in the codomain. No two are mapped to same. So this is an injective or one-one function. Whereas coming to the second example, now let us consider minus 1, 0, 1, 2. Here 0, 1, 2, 3, 4. Here both minus 1 and 1 are mapped to 1. According to the definition, this is not possible for an injective function. So f of x is equal to x square is not an injective function, as elements are not mapped to unique element in the codomain. Two elements are mapped to a single element in the codomain, so it's not an injective function. Okay, next, surjective or onto function. What is an onto function? So here surjective function is a function in which for every element in the codomain, there is an element in the domain. See, let's look here. For 1, 2, 3 and 4, for all the elements in this codomain set, there is an element in the domain set. But whereas in this example, no element from the domain set is mapped to 3. So this is not an surjective function. There is not necessary that only one element should be mapped to one element in the codomain. Here, see, there are two elements mapped to 3. Even this is also considered, but there must be at least one element from the domain set mapped to every element of the codomain set. Then that is considered as a surjective function. Next, bijective function. Bijective function is a function which is 1, 1 as well as onto. That means every element in the domain set is mapped to unique element in the codomain set, and unique element in the codomain set, and every element in the codomain set have an element in the domain set as well. So here we see an example. Every element is mapped to unique elements in the set B, as well as for every element in the codomain set there is an element in the domain set. Whereas the following examples, here 3 is not having an element in the domain set. B and C are mapped to 2, here 4 is not having an element and 3 is mapped to 2 elements. So this is not examples. So these 3 are not examples of a bijective function. Next, identity function. Identity function is a function in which every element of the domain is mapped to itself. So that means, let's consider an example. 1, 2 and 3. 1, 2, 3. So 1 is mapped to 1, 2 is mapped to 2 and 3 is mapped to 3. So every element of the domain is mapped to the same element. That is called an identity function. Example for this identity function is f of x is equal to x. Here the value of x and f of x is same for all the x in the domain. The graph of y f of x is equal to x function is a straight line. Next, coming to a constant function. Constant function is a function in which no matter what the input value is, the output value remains the same. That means for every element in the domain, it is mapped to a single element in the codomain function. So let's see an example. This is a domain and this is codomain. Every element is mapped to itself. Then that is a constant function. For every element in the domain, the element in the codomain is to which it is mapped is same. So this is the example, y is equal to 2. Here for all x values, the y value is same. This is a constant function. Next, polynomial function. A polynomial function is said to be a polynomial function if for each x in R, for each element in the real number line, if y is equal to f of x is in the form a naught plus a1x plus and so on an into x power n, where n is a non-negative integer and a naught, a1 and so on an belongs to real number line. So the graph of this type function is a parabola. So basically for all x in a given domain, the element in the codomain must be of the form a naught plus a1 x plus a2 x square plus and so on plus an x power n, whereas a naught, a1 and so on up to an belongs to real numbers. So the element in the codomain must be in a polynomial form. Then that is considered as a polynomial function. Coming to rational function. Rational function is of the form f of x by g of x, where f of x and g of x are two polynomial functions. So basically rational function is f of x by g of x. It is defined as fraction of two polynomial functions, whereas g of x is not equal to 0. G of x must not be equal to 0. Then that is considered as a rational function. So rational function is of the form f of x by g of x. So g of x is not equal to 0. Then it is a rational. Next, coming to modulus function. A modulus function, the definition given here is wrong. A modulus function is a function in which gives non-negative integer regardless whether the input is positive or negative. That means for an element in the domain, whether it is a positive one or a negative one, the value in the codomain is negative. So let us consider y is equal to mod x. So domain is 0 and the codomain is 1 and 0. Here we are just taking some part of domain and codomain. Okay, so now -1 is mapped to 1 and 1 is also mapped to 1. 0 is mapped to 0. Regardless whether the input value is negative or positive, the output is always positive. So the modulus function is also known as absolute valued function, which means it gives the absolute magnitude value of a given input value. Next, signum function. Signum function is defined as f of x is equal to -1, 0 and 1 for x less than 0, for x is equal to 0 and for x greater than 0. So that means if we consider 1, 2 and 3, -1, 2 and -1, 0, 3, -1, 0, 1. So for the values which are less than 0, f of x value is -1. If x value is 0, then f of x value is also 0. If f of x value is greater than 0, x value is greater than 0, f of x value is equal to 1. This is known as signum function. So here the definition of the signum function is given. The domain of the function is R. R means the real line, but the range is just -1, 0 and 1. Next, greatest integer function. So greatest integer function is defined as f of x is equal to x in square brackets, x belongs to R. This assumes the greatest integer value that is less than or equal to x. So such function is known as greatest integer function. That means if x is equal to 2.3, greatest integer function of x is 2. That means the value will assume the greatest integer which is less than or equal to that particular number. So x is 2.3, x is 2. So for both of these numbers, greatest integer function is 2. So it attains an integer which is less than or equal to the number. Okay, the graph will look like this because see, from x 0 to 1, in between all the values are greater than 0, greater than or equal to 0 and less than 1. That means greatest integer function for all these values will be 0 itself. And next we are considering 1 to 2. Then all the numbers in this particular range are greater than or equal to 1 and less than 2. So that means greatest integer function for all the numbers in this particular range is 1. Okay, similarly for 2 to 3 it's 2. For 3 to 4 it's 3. Okay, this is also considered as this is also known as step function. because the graph of this function is looking like a staircase steps manner. This is also known as step function. That's all for today, guys. Today we have discussed about sets, relations and functions in detail. Thank you.